Hello everyone. Today we are going to derive the governing differential equation of a cantilever bar subjected to uniformly distributed axial load by equilibrium method. I have already derived the governing differential equation for a cantilever bar subjected to uniformly distributed axial load by defining stress on a small element. The video link is given in the description below. So to begin with, let us imagine a cantilever bar. So just remember that it is a cantilever bar, not a cantilever beam. If it is a cantilever beam, it will be subjected to transverse loading. Because it is a cantilever bar, it is actually subjected to uniformly distributed axial load. So we could see that the load is acting along the axial direction, and the load is not going to act along the vertical direction, along the transverse direction. If the load is acting along the transverse direction, you should call it as a beam. So first, let me define the geometric properties of this cantilever bar. This cantilever bar has got a length of magnitude L. It has got a cross-sectional area of magnitude A. So these two are the geometric properties that we are concerned with respect to this cantilever bar. This cantilever bar is made up of material that has got an Young's modulus value of magnitude capital E. And of course, this cantilever bar is subjected to uniformly distributed load that is denoted by Q, and its unit is Newton over mm, or it can be Newton over meter, depending on whatever unit would be conducive for you to work with. Okay, so I have clearly defined the geometric properties: length and cross-sectional area. Length can be measured in mm, cross-sectional area in mm square, and the material property, that is Young's modulus, it is Newton over mm square, that's the unit. And of course, this cantilever bar is subjected to uniformly distributed axial load that is given by this red little arrows there, and its unit is Newton per mm. This particular physical scenario and the physical scenario of little guys clinging onto the ceiling, both are the same. So let me draw a ceiling here, and you could see that some little guys are clinging onto the ceiling. So that's the first guy. The second guy is clinging onto the foot of the first guy, and the third guy is clinging onto the foot of the second guy, and the fourth little one is clinging onto the foot of the third guy, so on and so forth. Okay, this physical scenario and this physical scenario will be the same. Okay, so if you look at this particular physical scenario, the first person, he is going to experience the weight of his own weight and also the weight of all the four persons beneath him. Okay, and the second guy, he is going to experience the weight of the the second person is going to experience the weight of his own weight and also the weight of all the three persons beneath him. And the third guy is going to experience his own self-weight and also the weight of the two persons beneath him, so on and so forth. So if that is the scenario, you could see that the first person is going to experience the maximum weight, and the foot of the last person will be experiencing the minimum weight, which means that the strain, if you try to define the strain at the foot of the last person, it's almost going to become zero. So these two physical scenarios are going to be exactly the same. So I will try to represent a bar here to represent this physical scenario and this physical scenario. So this is like a cantilever bar that is subjected to uniformly distributed axial load. Now what I'm interested in doing is I'm interested in a small region of length dx, and this small length dx is considered at a distance of, let us say, x from the left extreme end. And this small portion, let me take this small portion and let me represent this small portion separately. So this is the small portion. Now In exactly the same manner, I can represent the small portion here. Okay, this is the small portion that we are interested in. Okay, I could highlight that. The guy that we are interested in is this guy. Okay, let me shade it. So this is the guy that we are interested in. And of course, the length of the small portion is dx. And it is considered at a distance of x from the fixed end. Okay, so I'm going to take this guy, and I'm going to draw this guy separately. So take this fellow and draw this fellow separately. So here we go. So let me only bother about this guy, and I'm going to take him and I'm going to draw him separately. Okay, so here is our guy. Okay, now if you look at this little one, let us assume that we will give a name to him. We will call him Alan. And we will assume that all the other guys above Alan and all the guys below Alan are going to be invisible. So the people above Alan, they are invisible. And the little guys below Alan, they are also invisible. Just imagine that if that is the physical scenario, even they are invisible to everyone, even including Alan, they are invisible. So only Alan is actually visible. Okay, if that is the physical scenario, then a person who is actually going to look from outside, he is actually going to see Alan floating. But only Alan will know that he is actually experiencing the weight of all the persons beneath him. So I'm just writing, Alan is going to experience the weight of all the persons beneath him. And Alan is also going to experience his own self-weight that can be denoted by this little arrows. We know that this Alan is very small and his height is dx. Okay, now because Alan is experiencing a weight of all the persons beneath him that is represented by this arrow here, and also the weight of his own body that is represented by the little arrows here. And you could see that all the weight are pulling him downwards, but Alan is not moving downwards because there is a reaction that is actually maintaining Alan in the equilibrium position. So there is a reaction here. Okay. So you know that all the action, this is one action, the weight is one action, so I can call this as action 1, and the self weight is another action, so I can call this as action 2. So the reaction, the total reaction should be equal to the total action. So the reaction should be equal to action 1 plus action 2. Okay, so for now I will call this action as reaction as F, and I will call this action 1 as F plus df. It's not going to be the same as reaction because action 2 is there. Okay, so action 2 is simply q into dx. Okay, so that's the total self weight is given by q into dx. So if that is the physical scenario, now I can use the equation of equilibrium. For equilibrium, the total action should be equal to the total reaction. Okay, so the total action is F plus df. Okay, that is the total action. Action 1. And also there is action 2, which is the self weight, which is given by q into dx. That is the total load that is acting on this small region, that is q into dx. Okay, q is the rate of loading per mm, and if you want to find the rate of loading over a length of dx, then it is q into dx. Okay, so this is the total action, and that should be equal to the total reaction, which is simply F. Okay, now I just want to do one change to this equation. What is the change that I'm going to do? I'm going to multiply and divide by dx. So if I multiply and divide by dx, I'm not going to do any damage to this equation if I simply multiply and divide by dx. So let me multiply and divide by dx. So I'm just going to multiply by dx and divide by dx. Okay. So I'm not doing any damage to this equation. Now we can see that this f on the left side and the f on the right side, they go away. Okay, I'm multiplying and dividing by dx because you see that this force is f here, and this force is f plus df here. So they are separated by a distance dx. So just to indicate that it's just a mathematical convenience, even though mathematicians will not allow you to say it that way. It's just multiplication and division by dx. Okay. So in the next step, you can see that it's going to be df by dx into dx plus q dx should be equal to 0. And in the next step, I can just divide by dx on both sides. So that enables me to cancel this dx. So I'll be left out with df divided by dx plus q is equal to 0. And I know that this is force that is acting, the resistance. We know that stress is internal resistance offered by the body against deformation. You can see that this is the resisting force. So I can shade the resisting force. So the resisting force is this force. So I'm shading it. So F is the resisting force. So I can say if F is the resisting force, then the resisting force is stress, internal resistance offered by the body against deformation into the cross-sectional area. So that is the expression for F. Okay. All right then. So I can just simply plug it here. So I will be getting in this equation, it's going to be d by dx. Mathematics is just like moving objects. So take this value of F and plug it here. You'll be getting sigma into A plus Q is equal to 0. I know that the cross-sectional area is constant. I can bring it outside. So I'll be getting A into d by dx of stress plus Q is equal to 0. I know that Young's modulus is simply stress divided by strain. So I should say stress is equal to Young's modulus into strain. Mathematics is just like moving objects. So I'm going to take this value of stress and I can plug it here. So I'll be getting A into d by dx of Young's modulus into strain plus Q should be equal to 0. I can bring this Young's modulus common outside. So it's AE into d by dx of strain plus Q is equal to 0. So this is the strain of the small portion. And you could see that this is a strain of the small portion that we are concerned about, which means the small little guy, Alan. And also it is equal to the small portion that we have considered that is subjected to small little uniformly distributed load, that is Q into dx. Strain is if this portion gets displaced by an amount U1 and this portion gets displaced by an amount U2, and the distance between them is, let us say, del x. The strain is change in length, which is U2 difference U1 divided by original length, which is del x. For very small values, then that becomes equal to del u divided by del x. For very, very small values, we can say that du by dx. Okay. So that's basically the definition of the strain. And you can see that it's oriented vertically, but in actual case, the bar is oriented horizontally. So you can basically define strain. It is u1, it is u2, this distance is del x, so it's du by dx. All right then. So you know that strain is du by dx. You can take this value of strain and you can plug it here. So you'll be getting A into d by dx of du by dx plus Q is equal to 0. So you'll be getting A into d square u by dx square plus Q is equal to 0. So that's the governing differential equation of a cantilever bar that is subjected to uniformly distributed axial load by equilibrium method. Okay, so the boundary conditions are very simple. At the left extreme end, the value of displacement is 0, and at the right extreme end, which means at x is equal to L, you could see that the last person's foot is not going to experience any strain at all. So we can say that du by dx should be equal to 0 at x is equal to L. So these two are the boundary conditions. Okay, hope this is useful. So thank you all for your patience.